All right, so we're about to begin a new chapter here, and I want to just go over a little bit of an overview about what are our basic goals for things we want to accomplish. By in the end, we're going to do a lot of math, but what is it that we're actually after? There's usually like one of two things really when you really like look at it carefully. We're either looking so if we have some fluid flow, we're either looking for a high level of detail, like I want to know the velocity patterns or the pressure distribution within a system, and maybe even how it evolves over time, if it's a transient flow or a turbulent flow or something like that. So in some situations, we really want to know everything about a flow pattern, which requires a lot of detail. But in other cases, since we're engineers, we're often actually only interested in some aggregate behaviors of a system, things that we need to design against. So for example, if I have a given flow pattern, I might not actually care about the flow pattern as much as I care about any forces or moments that it imparts on objects that it touches. Or if I'm trying to choose the size of a pump or something like that, I might be less interested in the flow pattern than I am in the total flow rate of things moving around in the system. Like flow rates are things that help you, come up with spec sheets that you can give to other engineers about like how they can expect to interface with your system. Most people don't need to know everything, every last detail of a fluid flow pattern in order to, interface with a fluid system. So these are two separate things, and they really lead to sort of two different schools of thought about like how we should proceed in order to get answers about, either the aggregate behaviors or the high level details of a fluid flow pattern. So in general, when we want these really high levels of detail, what we're going to need to do is come up with, basically we're going to need to formulate differential equations that define what happens point by point in a system. And when you're looking for what happens point by point, you end up having to write, whatever the equations of motion are on a pointwise basis. And so inevitably what'll end up happening, as we'll see, is that in order to get pointwise details or like spatial information about a system, we'll have to write all of our equations of motions for infinitesimal control volumes, which will give rise to differential equations, which we'll then have to solve. So that's obviously the method that involves the most mathematical complexity and isn't always necessary. So we're going to start a different way. We're going to start by using macroscopic control volumes. So we'll do F equals MA, but not not pointwise. We'll just do F equals MA for like a whole system of stuff and see how much information we can get by doing more macroscopic control volume approaches. So these macroscopic control volume approaches are basically what we're going to do for at least, maybe like the first or the next two chapters or so, I would say. Because you can really get a lot of information that way before you start doing trying to figure out what the exact flow patterns look like. In general, in either case, actually, the general approach here is to apply basically I'll call them the three laws that apply to fluids most commonly, right? Conservation of mass, conservation of momentum. So momentum, if you were doing conservation of momentum or F equals ma, let's say, in another class, the acceleration is a vector, so it's a vector with three components. So F equals ma is not one equation, it's actually three equations. So the same thing ends up happening in fluid mechanics. I wouldn't call it F equals ma. I'd mostly refer to it as like a momentum conservation. But there's momentum in the x direction, momentum in the y direction, momentum in the z direction. And so we'll apply conservation of momentum to get three equations of motion. And then occasionally, if we're interested in it, we'll apply conservation of energy. So conservation of energy is not always required, because if the only thing you have is kinetic energy, then actually kinetic energy is actually sort of built into F equals ma. You just if you multiply momentum by another velocity or dot it with a velocity, you get the conservation of energy right back. But if you have things like heat flows and you're adding work to a system and other things like that, then conservation of energy comes into play. So throughout the course, this is basically what we're going to do. So we'll apply these 5 conservation laws, right? Conservation of mass, conservation of momentum, and conservation of energy, to learn either aggregate behaviors of flow or high level of detail, meaning like the entire flow pattern.